Dear friend, here we have brought you a very interesting example on calculation for deflection for a cantilever beam which is subjected by a point load at its tip. Here, this is the first lecture and we have taken a very simple example. You can say it is the simplest example. There is a cantilever beam of span L and fixed end support is designated with A and free end is designated with B. And at point B, this is the tip of this cantilever beam which is subjected by a point load P. Now we are going to evaluate the deflections at this point B. The deflection calculation will be solved by four renowned method, which is mentioned here. Method 1 is unit load method. Method 2 is moment area method. Method 3 is strain energy method. Method 4 is conjugate beam method. We will solve the same example through all four renowned method, and through this example I will try to explain in detail so that your basic concept regarding all these four methods will be clear. And later on, this is the first lecture on the deflection calculation of cantilever beam, and later on I will try to calculate the deflection or maximum deflections for a cantilever beam subjected by various kind of loading like beam. This is a cantilever beam which is subjected by uniformly distributed load. Span will be L. There may be some cantilever beam which is subjected by a triangular loading, this kind of loading. There will be some cantilever beam which will be subjected by a triangular loading in this shape. This kind of loading is normally exists in the retaining wall structure or water retaining structures. And there might be some cantilever beam which is subjected by a trapezoidal loading. All kinds of example will be solved with in later lectures, but initially I tried to explain you with a very simple example for a cantilever beam which is subjected by point load at point B, which is tip of this cantilever beam, and will be solved by four methods which I have explained here. Now I will try to solve this problem using unit load method. This is the first method. Method first, unit load method. Problem statement is there is a cantilever beam of of length L. There is a point load P which is acting at its tip, which is designated as B, and fixed end point of this cantilever beam is A, and our objective is to calculate the deflection of this cantilever beam, that is delta. As we are going to calculate deflection at B, so we will designate it as delta B. Delta B is deflection at B of this cantilever beam. Now, from unit load method, we evaluate two moments. One moment is M1, which is for the deflection, which is for the moment calculated at a distance of x from the tip of this beam, and there is moment m2 which is calculated at a distance of similar distance x, but with a unit load applied at the tip of this beam. You can will explain here, but try to understand. Delta B is calculated with an expression from the unit load method, which is written something like this: m1 m2 dx divided by ei integral 0 to L. We need to understand what is m1, what is m2. m1 is moment at a distance sorry at a distance x from the point load P at tip of the cantilever beam, and m2 is moment at a distance x, which is same as that we have taken for m1, from the point load of amount unity, that is p equal to 1 at tip of the cantilever beam. Here we can express the same m1 and m2 in the following manner. This is P. Problem statement is that for the m1 we have to find out moment at a section of xx, which is at a distance of x from tip of this beam, and this is point B and this is A, and we need to find out moment at x, which is mx, which is in anti-clockwise directions. Now m1 equal to mx equal to load is P, and moment should be calculated at a distance of x from B, and so loading distance is x, so moment will be minus P into x. Our assumption is anti-clockwise moment should be negative. Assumption. Whatever assumptions, you can take your assumptions like anti-clockwise moment positive. It depends upon you, whatever assumptions you take. Now m2 is, according to this statement that I have explained in previous page, m2 is, this is for m1, for m2 same beam, same length, but load at tip is at its tip is 1, and we're taking moment at a distance of x. Some section is xx, same that we have used for calculation of m1. Now distance is x, so same distance x. Now load is 1, and we are going to calculate moment at a distance of x from this point B, and load is acting at a distance of x, so moment will be m2, and same moment will be mx. Mx will be minus instead of P we will take a value of load 1, that is 1. In this case of applying load P, we have taken P multiplying with distance x, load multiplying with distance is moment, and x, that is equal to minus x. Okay, now we have calculated m1 equal to px negative, m2 equal to minus x, and from the expression of delta B from the unit load method, m1 m2 dx divided by ei integral 0 to L, we can write here for m1 we can write this one minus px, and for m2 we can write here minus x. So 0 to L minus px minus x dx divided by ei. Now it will be 0 to L p minus minus plus, so px square dx divided by ei, taking p over ei outside from this integral, so p over ei will be coming outside of this integral, 0 to L x square dx. Integral of x square is nothing but x cubed by 3, p over ei x cubed by 3 ranging from 0 to L, so it will come as pl cube divided by 3 ei. So delta B will be pl cube divided by thrice ei. This is the deflections. Now we have calculated deflection for a cantilever beam using using unit load method. It has been calculated using unit load method. Unit load method. Okay, fine. Now we'll calculate this same deflection delta B using another method that is called moment area method. This is very easy. You can see through this example, and if you have gone through the moment area method, you have it's a very clear statement in a moment area method. The deflection at any point is calculated as the product or multiplication of area in a moment m over ei diagram and centroid of this moment m over ei diagram. Now if we draw bending moment diagram and m over ei diagram and respectively with centroid, you will able to understand very easily. The problem statement is same. This is the problem. Load is P, length of this beam is L, and this is the point A, this is B. We are going to solve this with our second method, that is moment area method. The second method. Our main objective is to calculate delta B. Now, if any cantilever beam is subjected with a point load P, so moment will be linearly varying. Okay, so at a distance of x, moment will be P minus Px. At a distance of L, it will be minus PL. At a distance of x, moment will be mx equal to minus Px. So beam is ranging from 0 to L, so mx at a distance of L which is, you can say it is MA. Moment at A will be minus P into L, because the length is L. So bending moment diagram will be this one. This is A, this is B, and this is the maximum bending moment diagram, which is P into L with negative sign, as bending moment is coming out at its support. This is the hogging moment, which is the bending moment, BMD, for this cantilever beam. Now, for calculating deflections at point B, we need to draw a M over EI diagram. M over EI diagram, that it is the M diagram. Now we need to calculate M over EI diagram. It means bending moment at every point is divided by the constant value, that is EI. So profile will be same, but its value will be somehow lesser than this, because we are going to divide the whole moment with a constant value of EI. So M over EI diagram will be somehow like this. The value will be PL over EI. At last point is PL, that is why if we are going to divide PL divided by EI, so it will be PL over EI. Span will be same, that is L. Okay. Now area of this M over EI diagram will be, area will be half, span is L, and height is PL over EI. This is the area of M over EI diagram. Now second step is to calculate the centroid of this M over EI diagram from the tip of this beam. This is the X bar. Now X bar equal to 2/3 of L, that is the span. We have to keep in mind the point where our objective is to find the deflection through this point, that will the benchmark to evaluate the centroidal position of any shaded area. Maybe it's a triangular or rectangular or any kind of shape, or maybe it may be a trapezoidal or parabolic, any kind of shape according to this problem. It is the simplest problem, so it is a rectangular shape, so its centroidal distance will be X bar. It will be 2/3 of this length from this tip of this beam. So X bar is 2/3 of this length. Now deflections delta B equal to area multiply with X bar. This is the area of this, area of the M over EI diagram, and this is the centroidal distance, centroid of M over EI diagram. So delta B will be half into L into PL over EI multiplying with 2/3 of L. Now 2 cancel, PL, L and L, it will be PL cube divided by 3EI. So delta B will be PL cube divided by 3EI. This is the deflection calculated at point B through moment area method. The same deflection we have calculated using unit load method, that is PL cube 3EI. the first method was unit load method. Second method we have used moment area method. Now we are coming with another method, that is called the strain energy method, to find the same deflection delta B for a cantilever beam. Method third is strain energy method. Method third, strain energy method. As you know, problem statement is same. Beam, cantilever beam having length L, loaded with point load P at its tip B, and our objective is to find deflection delta B, but using strain energy method. Yeah, actually in strain energy method you need to find out the strain energy, and the deflection is nothing. Delta B is the rate of change of strain energy with respect to load. Now delta B is, as per the statement of the strain energy, differentiation of delta U, differentiation of strain energy with respect to load P. You can say rate of change of strain energy with respect to P, load P. U is the strain energy. Actually, whenever you apply any load, or whenever a beam is subjected with a point load or a UDL or triangular load or any kind of loading, it undergoes deformations. There is some deflections. Due to this, some kind of energy is stored in this beam, that is called the strain energy, and this strain energy is having an expression of m square dx divided by twice EI integral 0 to L, because length is 0 to L. Now we need to find out, today it's an integral, so we need to find out moment at a distance x from the load P. So beam will be this one, load is P. We need to find out moment m at a section x at a distance of x, and moment will be mx equal to m. This is the m we need to find out. Now mx will be, it's very simple, there is a load, point load P, and which is acting at a distance of x from, so just moment will be load multiplying with the distance, so load will be P, but it is in anti-clockwise direction, so it will be minus Px. Okay, so just putting this value, and mx is nothing but m, that is this expression which is used in a strain energy theorem. Therefore U will be 0 to L. In place of m you can directly put minus Px d Px square dx divided by twice EI. Now 0 to L, it will be P square x square dx divided by twice EI. It will be 0 to L, taking P square divided by 2I outside, P square divided by twice EI outside, x square will be inside of this integral, so P square divided by twice EI will be this one, and integral of x square will be x cube divided by 3, and it will be ranging from 0 to L, so P square L cube divided by 3 multiplying with 2 will be 6 EI. This is the strain energy. This is strain energy we have calculated. This is the strain energy. Strain energy. We know the rate of change of strain energy with respect to load is the deflection delta B. So as per the statement of deflections, for deflection calculation through strain energy, delta B will be the rate of change of strain energy with respect to load P. But to calculated strain energy is strain energy U equal to P square L cube divided by 6 EI, which I have calculated here. This is strain energy, P square L cube divided by 6 EI. Therefore delta B will be differentiation of strain energy with respect to load, P square L cube divided by 6 EI. Here length is constant, E flexural rigidity is constant, so it will be coming outside. L cube divided by 6 EI will be outside, so differentiation with respect to load, P square, and differentiation of P square will be 2P. Now it will be 3, so it will be PL cube divided by 3EI. This is nothing but deflection delta B. Nothing but deflection delta B. This deflection has been calculated using method of strain energy or strain energy method. Strain energy method. Deflection calculated using strain energy method. Now we are going to move with the another method, that is the last method, which is conjugate beam method, and it is very easier method if you understand the concept of conjugate beam. How you need to understand how any real beam is converted into conjugate beam, then your problem will be very easy. Now same problem, analyzing the same beam, calculation for deflection delta B using a method called as conjugate beam method. Conjugate beam method. Problem statement is same. Load is P acting at a distance of L from the support A. We are going to find out the deflection delta B. This is our objective. But this time we are going to find this deflection delta B using conjugate beam method. Now any beam, you can take this same example here. This is the point load P. This is the fixed support. This is the fixed support. What is this? This is the fixed support. Fixed support. This is tip of this beam is a free support. You can free end. You can say it's free end. You can say this is a real beam because we are analyzing this beam, so we are going to call it a real beam. Real beam. Conjugate beam is nothing but an imaginary beam. Through this we are going to calculate the deflections. So the corresponding conjugate beam of this beam will be, as per the statement of conjugate beam, any fixed support will be a free end, and any free end will be a fixed support in a conjugate beam. Conjugate beam, you need to go detail with the conjugate beam statement through any textbook or any literature. Conjugate beam of this real beam will be, because this is a free support, free end, so it will be a fixed support, something like this, and this is a fixed support, so it will be a free end. But its designation, that will be A and it will be B. It will be A same, but it will be B. Now as per the statement conjugate beam, this is the delta B. We need to calculate delta B. From the statement of conjugate beam, delta B is nothing. It is the bending moment. Delta B is the bending moment. Delta B in a real beam will be the bending moment in the conjugate beam in the same point, at the same point. For example, we are going to find the deflection at any point B, then the corresponding bending moment at point B of the conjugate beam will give directly the delta B. If we are going to find out deflection at point, suppose this is the point x, y, z, you can take anything. Suppose this is the point z. The bending moment at this point z will directly give the deflections. This is the deflection y, suppose this is the yz, that mz will give deflection yz. This is the deflection yz. This is the mz is the moment at point z, moment at point z in conjugate beam. And so we need to find out the bending moment at point B. Now, how the loading diagram is put on the conjugate beam, we have to understand this one. This is the real beam which is subjected with a point load P. Now we have drawn a conjugate beam. Fixed support of this real beam has been converted with a free end, and free end has been converted with a fixed support in a conjugate beam. This is the conjugate beam. This is the real beam. This is the load at its tip. But what will be the loading pattern in this conjugate beam? As per the statement, for the solution of deflection using conjugate beam method, we need to find out, we have to evaluate first the bending moment diagram for a real beam. The bending moment diagram for a real beam will be nothing but it will be something like this. Moment will be 0 and here moment will be PL, as we have calculated earlier in earlier examples. This is the maximum moment PL and span is L, length is L. Now through the conjugate beam method, the same we need to draw the M over EI. This is the BMD in the real beam. We need to calculate the M over EI diagram. We have also calculated M over EI diagram in a in moment area method. The M over EI diagram will be same, profile will be same. So PL over EI will be the M over EI diagram. M over EI diagram in a real beam. This M over EI diagram will be directly put on the conjugate beam to make a loading pattern on this conjugate beam. So the loading pattern will be something like this. This will be maximum value of PL over EI. Loading pattern will be something like this. Now loading pattern is done in the conjugate beam. Our main objective is to find out, this is the point A, this point is B, here same point will be not different. Now if we are able to find out MB, moment at B, at point B, it will directly give MB. If we are calculating, it will give delta B in real beam. Okay, delta B is the deflection in real beam. This is delta B, deflection in real beam at B, and MB moment in conjugate beam at B. Therefore we need to find out moment at point B. Here we need to find out the moment at this point. Now MB equal to, this is the loading diagram, this is the triangular loading. So area of this loading multiplying with the centroid will give directly the bending moment at point B. This is the span L. So load area of this loading diagram will be half into L into PL over EI. This is the area in this loading diagram, multiplying with the centroid will be, for this beam will be, since it is a triangular loading, centroidal distance x bar will be 2/3 of this length L. So load, this is the load, the centroidal x bar. So load multiplying with distance will give the moment. So half L multiplying with PL over EI x bar equal to 2/3 of L multiplying 2/3 of L. Now 2 cancel, it will be PL cube divided by 3EI MB equal to delta B. Hence moment at point B in a conjugate beam gives deflection at B in a real beam, which is equal to PL cube divided by 3EI. Same we have calculated through a conjugate beam method, and you can see in our 4 method: unit load method, moment area method, strain energy method, and lastly through conjugate beam method we have found out the deflection at tip of this cantilever beam is PL cube divided by 3EI. This is the simplest example I have brought you to overview all the concept for all these methods. Later on I will come with different complex loading diagram and will explain you with all these method. Now dear friend, I hope your concept might have clear, and I request you to share as much as possible and try to be connected with me and write down in our comment box how do you like this and in what areas we can improve. And I will also put a link for the PDF of this lecture that I have brought you, and we will always will be connected with another lectures. I will also intimate in our comment box when we will bringing another examples. So keep watching. Thanks a lot. Keep sharing. Thanks a lot, my dear.